Okay. All right. So what we're going to do today, everybody, is we're going to see somewhat of a small blast from the past, if you will. We're going to look at limits again, but this time we're looking at what happens when you have limits at infinity. Okay. Basically, this is taking something we learned in pre-calculus and showing you the reasons why it turned out the way it is. Basically, applying calculus to it. Okay. The other thing about it is this goes into kind of everything we've been doing up to this point, with the kind of using the derivative to figure out things about graphs, because this is the final piece we're going to use for a subject we're going to talk about beginning of next week, called curve sketching, which is essentially how to use all this information you get from the derivative, second derivative, etc., to draw a graph, if you will, or go from a graph to a function. Okay, but part of that is limits at infinity. Okay, limits at infinity are generally fairly simple. What they do to you, they do one or two things. They tell you either end behavior, or they tell you the location of a horizontal asymptote. Okay. Now, there's before I go any further, there's going to be like kind of one definition we're going to want to use, or kind of one property we're going to want to use. Kind of a quick theorem here, and it's basically we'll call it the I don't know what to call it. Quick theorem, I guess. Quick idea. Okay. Basically, and if if R is a positive number and C is a constant, then, okay, the limit as x goes to either plus or minus infinity, doesn't matter which one, of C over x to the r is always equal to 0. Okay? Basically, this is saying something we've already learned long ago, which is if I divide something by infinity, I get 0. Okay? So if I divide a constant number by infinity, it always comes out to be 0. Okay? Technically speaking, this is actually what you're doing anytime you do that. Okay? Remember, this is something very important. Okay? Infinity is not actually a number. Okay? So if I'm doing work with infinity, what I'm actually doing is I'm taking the limit as the variable goes to infinity. Okay? Basically, all we're really saying is what happens when this system gets really large in either direction. Okay? Well, with a fraction, with a variable in the denominator, when the variable gets really large, what happens to the fraction? Does it get bigger or smaller? It gets smaller. In fact, it gets really small, doesn't it? Okay? And so the idea is if I can go far enough, okay, with making the denominator really big, eventually the fraction just becomes 0. Heck, some people, some old-timey calculators, if you kept dividing by the same number over and over and over again, eventually it would just 0 out. The calculator would just be like, all right, we're done, and it just gives you a 0. Okay? I always thought it was kind of fun as a kid to do that, but I was a special child, maybe. Okay.
Back when your best toy was a hoop and a strip and
a hoop, stick. Yeah. Ball in a cup, ball in a cup, it's a ball in a cup. Now, my toys when I was a kid were Legos mainly. I played with a lot of Legos. Okay. So I probably would have loved Minecraft if it existed when I was a kid, but anyway. All right. So when we're looking at limits at infinity, basically we're going to have one of three situations arise. It all depends on, basically, you're going to treat every function of this type like a rational function, even when they aren't. You're just going to think of them like a rational function. Okay? And if you remember, there were three conditions that rational functions had. Okay? And it all had to do with whether the numerator had a larger degree than the denominator. Okay. And if you remember from pre-cal, that determined whether you had a horizontal asymptote or oblique asymptote. And also determined how you find your horizontal asymptote. Well, basically, limits at infinity are going to do the same exact thing. But what we're really doing is just formally saying why those rules for asymptotes apply, basically. And why this is useful is you'll get questions on the AP. They're really simple, but they always throw people for a loop. Because they'll be like, find the horizontal asymptote for this function. And people are like, well, I don't remember seeing horizontal asymptotes. What gives? Well, it just means take the limit as x goes to infinity. That's what they're asking for. Okay? Or as x goes to negative infinity, because you can have graphs with two horizontal asymptotes. Okay? But basically, the basic rules is as follows. Okay? Basically, think of functions as being in the form f of x divided by g of x, okay, like so, okay, with basically rational form, right, okay. The difference is we're going to think of all functions as being this way, okay. Now, we could do that because we could always just say for a function that's like x squared, and not clearly that's not a fraction, well, I can always write it as x squared over the constant function 1, right? And then it's in this form here, okay? But anyway, start to think of all functions like this, okay? Then one of three conditions arise, okay? First condition, okay? Basically, if the degree of f of x is less than the degree of g of x. In that condition, okay, the limit as x goes to plus or minus infinity, okay, of the function, we'll call it y up here, so let's call it y, it's always equal to 0, okay? So, if the bottom has a degree that's bigger than the top, the thing always converges to 0, okay? Or at least the fraction part always goes to 0, okay? If there's like a constant added on, then obviously it goes to that constant. But basically, that's what we're getting at there, okay? That's our first case, okay? Our second case is if the degrees of f of x is equal to the degree of g of x, okay, then the limit as x goes to plus or minus infinity of the function is equal to some constant, okay? And k for constant, because of course constant starts with a k. Alright.
Tough crowd.
Yeah, tough crowd. There's an absolutely hilarious thing from the show Robot Chicken.
Oh God.
Where they're making fun of a really old 80s cartoon show called Mask. And Mask is, in the show is supposed to be an acronym, Mobile Armored Strike Command. So they're spelling command with a K instead of with a C. Okay? It's very stupid. The show is very stupid. But Robot Chicken has this, like, they make fun of it with like the theme song with replacing the lyrics. And one of them is like, Mask, don't they know command doesn't start with a K? And it's rather funny. The whole thing is really funny. Anyway, one of these days I'll show it to you all. Anyway.
When we're old enough, right?
Oh yeah, absolutely. No, there's nothing in it that's bad. It's just hilarious. Okay. All right. So that's our second case. Okay. If the degree of f of x is equal to the degree of g of x, then the thing is going to be equal to a constant. We'll look exactly how you figured that out here in a moment. Okay. The last situation, because we're going to look at all three of these examples. Okay. Our last situation, okay, is if the degree of f of x is greater than g of x, degree of g of x, okay, then the limit as x goes to plus or minus infinity does not exist. Okay, it diverges. Okay, is the proper term for it. Okay, you're not going to see that though in the AP, but the actual term we would use is it diverges. Okay, this last case, by the way, This one will explain, or it will show, but you can use this to demonstrate end behavior. Because while it does not exist, okay, while the limit does not exist, you can figure out generally what the sign of the thing is, and that will tell you whether you're going upwards or downwards as you go that way or that way, okay? So that's something to keep in mind. Again, we'll look at an example of this, okay? Does everyone have all three conditions down?
Could you scroll like the first one?
First one, that one. Okay. Yep. So it would be 0, a constant, or it doesn't exist.
Yeah, I haven't flipped, so I was a little
Okay.
confused.
And technically speaking, too, these are just for the fraction part, not for any other part. So if you had a more complex function, things would be different, okay? But for the thing divided by the other thing, these are the rules, okay? And you could get some other situations. Like I said, you could have like 2 horizontal asymptotes, things like that. We'll look at examples of that later. It's not really that big of a deal. And again, it all depends on when you look at the thing going positive or negative infinity, that sort of thing. Okay. All right. Great. Now get the masks on stuck in my head. It's very catchy. Okay. Let's scroll down a little bit. Good so far? Okay.
Can I open this window?
Yeah, you can absolutely open the window.
It was 32 this morning.
Yes, it was. Car was covered with ice.
No.
Yep.
What?
You pop for women to get here?
No, I hate winter.
I love it.
I like fall and I like spring. If I were to rate my seasons, fall, spring, summer, winter.
Really?
Yes.
Okay, come on, help there.
Winter, fall, spring, summer.
Spring, summer, spring, fall, winter.
I can mean it, son.
Fall is just like,
There it is.
What is my favorite?
I like fall because the weather mid-fall turns into like perfect weather for me. Okay, where it's like cool at night but not cold, and it's like warm during the day but not hot. It's like when it becomes weather, that's when I'm very happy. But then when it gets too cold and you have to put on a coat, and it's like no good. Anyway, all right, let's look at examples of each of these cases. Okay, just so you can see how they work. Okay, first case. Okay, first example would be something like the limit as x goes to negative infinity of 3x squared minus 2 over x cubed plus 4 minus 3. Okay? Now, here's something I've been harping on throughout this entire lecture is that the limit as goes to the limit part only affects the fraction. Doesn't do anything else that's tagged on the end. Okay? So, if I were to do this limit, what's going to happen in this fraction here?
It's going to go to 0.
It's going to go to 0 because the bottom has a larger degree than the top. Okay? Basically, think of it this way. The bottom is growing faster than the top does. So even though, technically speaking, if I were to throw infinity in here, I get infinity over infinity, which you're not supposed to ever get. The bottom is getting bigger faster than the top is, and so the thing should go to 0 still. Okay? So if I work this out then, this would become 0 minus 3. So what's my answer?
-3.
Negative 3. And if I'm graphing, this negative 3 here is a horizontal asymptote. Okay? And because that's what you would get. Okay? Where does it go as I go into infinity? It approaches negative 3. That's the definition of a horizontal asymptote.
How do you know if it approaches from above or below?
Oh, for that you would have to do other points and things. Okay?
Okay.
You would have to look at it more towards the origin. But you just know as I go off to, as I head off to negative infinity, I should end up with negative 3. Another way to test to see if it approaches from above or below
Could you do
is
like
to see what the sign should be of the thing.
Yeah.
The top x squared, negative infinity is going to be positive, but the bottom is going to be negative, so the
it's
whole thing is negative.
Okay.
So it should approach from below. Okay. That's the idea though.
Come a long way with pilot depths and everything.
But there's a rule I have, he just broke it.
What's that?
Don't come late on Saturday.
No, it's just my cast. I'm playing my costume. I'm
We'll
playing
talk
the
after class.
dissenting
Anyway.
teenager.
Limit as x goes through. Okay, so the second case is when they're going to be equal to each other. Okay, the degrees are equal to each other. So limit as x goes to infinity of something like 5x plus 3 over, we'll say 2x minus 4. Okay. Here the degrees are equal to each other. So this thing should, when I take the limit of it, be equal to some sort of constant. Okay. All right. In this case, you're figuring out what that constant is, you're going to do an extra step here. Now, we remember from pre-calculus that the constant this thing will go to, the horizontal asymptote, is going to be 5/2, right? That's what we remember from pre-cal. How we figure out it's 5/2, though, there's two ways I can do it. One is, I can actually do the polynomial along division here, okay? And I'm going to get 5/2 plus some fraction where the denominator is going to be 2x minus 4 and the top is going to not be 2x minus 4. It's going to be something small, going to be degree smaller. And then when I take the limit as x goes to infinity, it goes to 0. Another way I could do this, though, is to rewrite the whole fraction a little bit faster than doing the polynomial along division as 5x plus 3 over x divided by 2x minus 4 over x. If I'm dividing by the same variable on top and bottom, can I do that? Of course I can. It's just 1. Just multiplying the thing by 1. I can, of course, do this. Well, the benefit of this, then,
The x cancels.
is the x's cancel. So I can rewrite this as 5 plus 3 over x and 2 minus 4 over x. Okay? Is what I would end up being. And now when I take the limit as x goes to infinity, what's going to happen to those guys?
0.
They go to 0. Okay? And I'm writing this completely wrong. If this was an AP, I would have lost credit there.
My
And
God.
as x goes to infinity. There we go. Of 5 plus 3 over x.
How could you?
Divided by 2, what is it, minus 4 over x. And what's that going to be equal to? 5/2.
Right.
So, if you've ever wondered why we were looking for horizontal asymptotes, we just do the leading coefficients. This is why. Okay? It's because actually the limit ends up going there. Okay? Any questions about this last case here? Yet. And again, if I wanted to know whether it approaches from above or below, I just look generally what the sign should be. Top it's positive, bottom it's going to be positive, so it's positive. It's approaching from above. Okay? Alright, final case with limits at infinity, okay, is when, of course, the top is bigger than the bottom. I'll say minus infinity of x cubed plus 2x squared minus 3x plus 4 over x squared minus 8. And the limit here does not exist. Technically, it's going to go to negative infinity. Okay. Now, how do I know it's negative infinity? Well, I know the limit's not going to really exist because the top is so much. It's going to have a larger degree than the bottom. 3 is bigger than 2. Okay. And because 3 is bigger than 2, the thing will diverge. It won't go to any point. Okay. It just shoots off into infinity. Okay. How I know it should go out, the end behavior should be towards negative infinity, again, I look at what the sign should be. If I plug negative infinity into this thing, x cubed is going to be negative, x squared is going to be positive. So negative over positive is negative. So it should go to negative. It should go off to negative infinity. Okay? In that direction. Alright. So, that is how limits at infinity work. Any questions? Nope. By the way, your hat, I don't know, you've got that symbol on the top of it.
Mm-hmm.
It looks like an infinity symbol, which is perfect for this class. I like it.
Some
stuff.
kind of,
Totally planned that.
Came prepared.
Totally
some
planned.
kind of like
You knew it.
farming company.
Alright. Any questions about limits at infinity? Oh, it's a fairly simple exercise. Okay, everybody.